What's up, everyone? Today we're talking about liquids and solids, and we especially talking about what makes them special when it comes to chemical structures and chemical characteristics, right? So we usually observe these physical characteristics of what makes a solid or a liquid. So today we're going to explore really when it comes to the molecular level why you have liquids and why you have solids. So let's start with liquids to begin with. Right? So there are a few things that we're going to need to know, a few qualities, if you will, when it comes to liquids. The first one is the compressibility. Liquids, we know that gases are very compressible, and that comes from the fact that gases have huge distances between their molecules, but the liquids don't have distances between their molecules, and because of that it's really hard to compress them. Another property of liquids is viscosity, right? How viscous a liquid is, and we define this as a liquid's resistance to flow, right? So you know that whenever you pour out water versus when you pour out oil, for example, it's going to be different, and that's viscosity. Another thing to note about this viscosity is that it increases when it decreases when you increase temperatures. Whenever you heat something up, it becomes less viscous, right? Another one that's pretty interesting that we're going to look at is called surface tension. And surface tension refers to the attractive forces on the surface of a liquid, right? And different liquids have different surface tensions, all right? Another one that's really interesting that we like is called vapor pressure. The vapor pressure, we define it as the pressure exerted on the by the vapor at equilibrium at a specified temperature. Right? We'll talk more about the vapor pressure, but vapor pressure is another important characteristics when it comes to a liquid. Right? So you know about the boiling point. The boiling point is the temperature at which a liquid will turn into a gas. That's the boiling point, right? So when it comes to vapor pressure, is the temperature at which the vapor pressure of the liquid will be equal to 1 atmosphere. So we define a boiling point as the temperature at which the vapor pressure of the liquid will be equal to 1 atmosphere. So that means that the vapor pressure is 1 atmosphere when you have a normal boiling point. So the conversion from a liquid to vapor, when it is at a temperature below the boiling point, we call this evaporation, right? So when you're converting back from gas to liquid, we call this condensation, right? So those are a few terms, the ones that I have in red are the few terms that we're gonna need to remember and to know how to define when it comes to the properties of liquids. Another important part when it comes to liquids is the intermolecular forces. So we talked about gases, and the gases are so far apart that we don't have really any attraction between them. But the liquids, on the other hand, are attracted to each other. And that attraction is what we call intermolecular forces. Remember that we looked at the ionic and covalent bond, and these are really strong bonds. We call these intramolecular forces, right? But these ones are intermolecular forces because they are happening between the molecules, right? And this is what gets the molecules of liquids closer together to each other and this is why we have a liquid. So when it comes to intermolecular forces, we also call them weak forces. We're going to have 3 or 4 different types. So let's change this 3 into a 4, because we're going to have dipole-dipole interactions, London dispersion forces, hydrogen bonding, and ion dipole, right? But dipole-dipole and London dispersion can be classed as Vanderwald forces. It's okay. Now I will explain what each one of them is, but you can use this nice table that I found that will tell you which one, like pretty much what these all mean. But let's look at the Vanderwald forces. The Vanderwald forces are the attraction between the molecules based on their polarity. What does that mean? It means that, remember when we looked at whether something is non-polar or polar, right? We say that, it has implications in physical properties. That's what we meant. If something is polar and something else is polar, they are going to attract each other, right? So a quick review of the polarity. Right? So the polarity comes from, for example, if you have 2 molecules, let's say you have HCl, right? You have an HCl molecule, right? These 2 elements have a big difference in electronegativity, that one is pulling and the other one is pushing, and because of that you have polarity. And this polarity, we call this a polar molecule, right? And we say that this is a dipole because you have 2 poles. It's a dipole, 2 poles. Now if you bring another molecule that's also polar, that has also dipoles, that has a negative and positive side, they're going to attract each other. So this is a intermolecular interaction because you have 2 molecules, and this is a dipole-dipole interaction, right? 2 dipoles interacting is a dipole-dipole interaction. All right, so this is one of the types of Vanderwald forces that's called dipole-dipole interaction. The other type of interaction, so we have 2 types of Vanderwald forces. One is dipole-dipole interaction. The other one is we call London forces or dispersion forces, and these are the interaction between non-polar molecules, right? The interaction between non-polar molecules are called London or dispersion forces. How do non-polar molecules interact with each other? Well, what happens is that even though they are non-polar, they are going to have what we call an induced dipole. So usually non-polar molecules don't have a dipole, but the electrons, because we know that every atom and every compound has electrons in them, the electrons can rearrange themselves in a way that would temporarily induce polarity. Even though this is an unpolar, we temporarily induce polarity. We call it an induced dipole. That's when you have London forces, right? So again, to recap a little bit, we have Vanderwald forces that are comprised of dipole-dipole and dispersion forces. Dipole-dipole is between the polar molecules. London dispersion forces is attraction between the non-polar molecules. Now let's go to hydrogen bonds. Hydrogen bonds are also dipole-dipole interactions, but they are special dipole-dipole interactions, and they are special dipole-dipole interactions because this dipole-dipole interaction involves hydrogen and another high electronegativity element, right? So the hydrogen bonds occur between hydrogen and either nitrogen, oxygen, or fluorine, right? So this is an example. You have a polar molecule. This is H2O, right? H2O, we know that it's polar. And when it is polar, the hydrogen of one molecule is attracted to the oxygen of the other molecule. So it's the positive side of this polarity being attracted to the negative side of the other polarity. And this is what we call a polar. It's a dipole-dipole interaction, but it's a dipole-dipole interaction involving hydrogen and a high electronegativity molecule that can be oxygen, nitrogen, or fluorine. And we call this hydrogen bonds. And hydrogen bonds are really, really important in nature. It's pretty much one of the reasons why we are alive. And, we'll talk more about that. But hydrogen bonds occur between hydrogen and oxygen, nitrogen, and fluorine. And these are special types of dipole-dipole interactions. All right, let's look at another one more. Another one is ion dipole. What it really is that you have an ion molecule, and remember that we know that ions are just charged atoms, right? So the attraction between an ion and a dipole, or between an ion and a polar molecule, is an ion dipole interaction. So we're going to look at these four intermolecular forces. Those are the ones that I want you to remember and practice. But going back to the hydrogen bonds, right? So this is an example of water, right? Water, and this is like a three-dimensional version of how it looks like. One molecule of water is bound to many other molecules of water through hydrogen bonding, right? The hydrogens are connected or attracted to the oxygens. But again, we also have nitrogen and we also have fluorine. So these three compounds are the only compounds that undergo hydrogen bonding, pretty much. But we'll talk about hydrogen bonding later when we talk about solids. But moving on to solids, right? Solids have a few spatial characteristics that make them different, right? First of all, we know that they have a fixed shape and volume, and this is different from your liquids and gases because we know that liquids occupy the shape of the container, right? They are incompressible, even more so than the liquids, right? And more importantly, they can be crystals, right? They are crystals that have regular repeating structure, right? That have no organized structure. Or let me look at different types. So if you look at solids at the molecular level, you're gonna find crystals. And there are different type of crystals. So if you can look at the picture on the right, those are different type of crystals. The first one is a diamond crystal. That's how it's organized. Those are carbon molecules, by the way, right? Carbon molecules are connected together like that. The second one is salt, sodium chloride, and it's made of as a cube like that. All right, and down there you have methane, and then you also have metals, right? D is a metal structure. So crystals can be ionic solids, they can be covalent solid, they can be molecular solids or metallic. And just to define this very quickly, ionic solids are made of ionic compound like sodium chloride. So we learned what an ionic compound is, and an ionic compound is a compound that's made of a metal and a non-metal, or a positive ion and a negative ion. Those are ionic compounds, they make ionic solids. Covalent solids are made of covalent compounds, and covalent compounds, remember that, are made of not non-polar molecules. They are made of non-metals, right? So not non pretty much it's a non-metal and a non-metal. Those are covalent compounds, right? Covalent solids can also be repeating structure of just one non-metal, right? So if you have carbon, for example, carbon repeating structure like diamond, it's a covalent solid. Molecular solids are, well, repeating structure of molecules, right? And then metallic solids are also what they sound like. They are metals, right? So if you have an aluminum foil, it's going to be just repeating atoms of aluminum, bunch of aluminum atoms together. Those are metallic solids. So these are all at the molecular level crystals, these crystal structures. Just like, we looked at how at the molecular level, the liquids get together with those four different types of forces that we talked about. But here is crystals, and these bonds can be ionic or covalent, right? So that's one of the reasons why the solids are so close together. The liquids have weak forces between them, but the solids have really strong forces, right? Ionic or covalent forces, but they are really, really strong forces. All right. So there is a special type of solid, right? We know that you have liquid such as water, you cool it down, you get solid, right? The solid is ice, and I wanted to talk a little bit about ice because ice is kind of very, very fascinating. I could talk all day about ice, but what makes it special, right? This is the structure. So you have hydrogen bonds, and on the left you have water, right? You have hydrogen bonds between water. You have just loose molecules of water, right? And on the right, you have ice. Ice are just these ordered, structured crystals of water molecules, right? And that's okay. That's okay. We already know this. We already know that, we have these intermolecular structures when it comes to liquids, but when we go to solids, they arrange themselves closer to each other into crystals. That's okay. But this special arrangement for ice, right, is responsible for most of life on Earth. And I'm not exaggerating. Why is that? If you go back to this structure, you can see that ice has more pockets in it. Ice has more pockets because it rearranges in a way such that it's going to have more pockets than liquids. So usually, if you take a liquid, you make it into a solid, it's going to be heavier and more dense. But the way water rearranges in ice cages, it turns ice, right? It makes ice less dense than water. That's a very, very important implication. Because of that, it makes ice float above water. And because of that, this is why you have pretty much have a lot of creatures that are in the sea are protected because of that. That's number one, right? Number two, if you go back to how our planet developed, right? This formation of ice had to be necessary for life to develop on Earth. If there wasn't any ice, all of it would have been destroyed. And if you hear about climate change and all that stuff, most of the things that they talk about center around what? Around the glaciers, right? and they're melting. Why is that? It's because this ice right here, floating above water, is pretty much what's protecting our planet, right? It's protecting our planet from heating and overheating. And this is all coming because ice can float on water. And this is because, going back to the hydrogen bonds, is because when water crystallizes, it makes a crystal structure that has more pockets than liquid water. So now when somebody asks you, hey, why does float above water even though it's a solid and water is liquid? Now you know what to tell them. It's about hydrogen bonds and crystal formation. All right. So one last thing that I want to talk about is you guys have seen this in high school, but we talked about changes of in states of matter. We talked about states of matter, but we didn't talk too much about changes, right? There's a whole area about how these change. And I gave you all of them here so that you can be able to study them. But the figure on the right is going to help you, right? So if you start with gas and then you go to liquid and then you go to solids, we have special names for each one of them, right? And it's just a matter of reading them and remembering them. Sublimation is really cool. It's a cool one because I don't know if any of you guys have seen sublimation, because it's a way you have a solid and it just goes from solid to gas without being liquid first, without melting first. And we can do that in the lab. I think I used iodine when I did it in the lab, but you can do that and it's really really cool. The position is the opposite, right? A gas becomes a solid. Freezing, we know freezing, we go from liquid to solid. Melting is the opposite. You go from solid to liquid. Evaporation is from liquid to gas. Condensation is from gas to liquid. So make sure that you remember these as well. But I think that's enough for the states of matter. I'll see you next time.